Hello lovelies, in this video we're going to go through the foundation content that you need for your Edexcel GCSE Physics Paper 2. Now, this might be your very last GCSE exam, so if you made it to this video, if we're still revising, then that is fantastic, well done. That shows you're going to do really, really well. Let's take a really low-key, really low-stress approach to this. So watch the video, try a few questions, have a look at the predicted paper, and then get ready for the exam.
I want to start off here by looking at prefixes. These are used throughout physics, through all of the topics, to describe the order of magnitude of a quantity. And when we're doing calculations, we need to make sure that we use the SI unit. So if they give you something such as milliamps, we need to convert it to amps. So we need to know that tera means times 10 to the 12. It's a very big number. Giga is times 10 to the 9, mega is times 10 to the 6, kilo is times 10 to the 3, centi, like centimetre, is times 10 to the minus 2, milli is times 10 to the minus 3, micro, which is this little Greek symbol, a bit like a curly U, is times 10 to the minus 6, and nano is times 10 to the minus 9. And you'll see here that I've highlighted out the centi one. And the reason I did that is I just want you to imagine, if that wasn't there, notice the pattern with the numbers. They're going down by 3 each time. This is a really easy way to remember these. So all you need to do is remember the order of these prefixes, and then you can work out the order of magnitude. So an example of how we might use this in practice is if we're told that we have 40 milliamps, for example, but we need to calculate something using that value, we will need to rewrite it in just amps. So in place of the M for milli, we write times 10 to the minus 3. So 40 milliamps is equal to 40 times 10 to the minus 3 amps. Please do make sure that you get these memorized. We need to know about energy stores and systems. A system is an object or a group of objects. We might refer to a closed system, which is a system when energy can't escape or enter the system. So closed systems are particularly important because in a closed system, the total energy remains constant. However, the energy may be transferred between its stores. So getting on to energy stores, we need to know the following ones. We need to know about kinetic energy, gravitational potential energy, elastic potential energy, internal or thermal energy, chemical, nuclear, magnetic, and electrostatic energy. So kinetic energy is the energy of a moving object. An example of this is a moving car. Gravitational potential energy is the energy an object has when it's raised above the ground. So an example of something with gravitational potential energy is a book on a shelf. Elastic potential energy is the energy an elastic object, for example a spring, has when it's stretched or compressed. Internal or thermal energy is the total kinetic and potential energies of all the particles within an object. An example of this is a hot cup of tea. Then we've got chemical energy. This is the energy stored in chemical bonds. An example of this is a battery or some food. Nuclear energy is the energy stored in the nucleus of an atom. An example of something that has this nuclear energy is the uranium fuel in a nuclear reactor. Then we've got magnetic energy. This is the energy that a magnetic object has when it is near to a magnetic field. An example of this is a fridge magnet. Then we've got electrostatic energy, and this is the energy that a charged object has when it is held near to another charged object. This can be seen in Van de Graaff generators. Energy can be transferred between different stores using 4 different methods. The first is heating. So energy will be transferred from one object to another if there's a difference in temperature, a temperature gradient, and it will travel from the hottest to the coolest. Radiation is another way we can transfer energy, and in this case the energy is transferred as a wave. An example of this is infrared radiation from the sun. Then we've got electrical work. This is the energy transferred by the flow of charge due to a potential difference. Finally, we have mechanical work. This is the energy transferred due to a force moving an object through a distance or changing its shape. So an example of an energy transfer is a book falling from a shelf. Initially, that book on its shelf had a gravitational energy store. However, that was transferred mechanically by the force of gravity to the kinetic energy store. We need to be able to say different energy transfers dependent on a scenario given to us in an exam. A force does work on an object when the force causes the object to move through a distance. The work done by a force on an object is given by work done equals force times by distance, where work done is measured in joules, force is measured in newtons, and distance is measured in meters. Of course, as always, we could use a little cheeky triangle here if you struggle with the algebra. If not, I would always recommend that you just rearrange this using the algebra that you've learnt in maths, but it's always good to have something up your sleeve in case you get stuck. If you did use a triangle, I would just pop a W on the top for work done and force times distance on the bottom. Now, we need to know that 1 joule is equal to 1 Newton metre. And this is because 1 joule of work is done when a force of 1 Newton causes a displacement of 1 metre. It's also really important that we know that work done against friction will result in a temperature increase. And this is why if you rub your hands together, they start to get warm, because you've done work against friction. Kinetic energy is the energy of a moving object. So the equation for this is kinetic energy equals half times mass times velocity squared. Or the simple equation of this is EK equals a half mv squared. So the units of kinetic energy is joules, the units of mass is kilograms, and the unit for velocity is meters per second. Gravitational potential energy is the energy gained by an object raised above ground level. To calculate the gravitational potential energy, we multiply together the mass with the gravitational field strength and the height. If we do this using symbols, then that's Eg is equal to m times by g, the gravitational field strength, times by the height. Now looking at units, gravitational potential energy is measured in joules, just like all of the energies are. Mass is measured in kilograms. Gravitational field strength is measured in newtons per kilogram. And height is measured in meters. Power is the rate at which energy is transferred. We can find the power in one of two ways. The first way we can use is that power equals energy transferred divided by time, or P equals E over T. Now remember, power is measured in watts, energy transferred is measured in joules, and time is measured in seconds. Alternatively, we could say that power equals work done over time. In this case, that's P equals W over T. Power is still measured in watts, time is still measured in seconds, and work done is measured in joules. We should know that an energy transfer of 1 joule per second is the same as a power of 1 watt. And we should also be able to compare different systems. If, for example, I was picking up a box and lifting it up to a certain height, the quicker I do that, the more power I have. The law of conservation of energy states that energy can be transferred usefully, stored, or dissipated, but it cannot be created or destroyed. And this is a really key fact in physics that we will use all the time. So when energy is dissipated, it is transferred to less useful stores. For example, if we have a light bulb, we take that electrical energy store that's inputted and it gets transferred to light energy, which is useful, but also thermal energy as it heats up. Now this thermal energy is the wasted energy or the dissipated energy. It's important that we know that all energy will eventually be transferred to the thermal store of the surroundings. In the exam, we might be asked how we can reduce unwanted energy transfers. There's 2 examples that they expect you to know. Firstly, we can lubricate it, and secondly, we can add thermal insulation. Those are 2 ways that we can reduce unwanted energy transfers. However, always have a think to the context of the question. For example, lubrication might be useful if we're talking about things rubbing over each other, because that will reduce the friction and therefore that thermal energy transfer that wouldn't be useful. However, I'm sure you can imagine that that wouldn't be useful for every example, so try and always think about the context and think, how can you reduce that unwanted energy transfer? The energy efficiency of an energy transfer can be calculated using one of 2 equations. Efficiency is equal to the useful output energy transfer divided by the total input energy transfer. So useful output over the total input. Alternatively, if we're given powers instead, we can say that the efficiency is equal to the useful power output divided by the total power input. So very similar idea. It's that useful output divided by the total input. Now, both of these equations, as they stand, will give our answer as a decimal. Now, in the exam, you might be asked to give your answer as a decimal or as a percentage. If we needed to get the efficiency as a percentage, all we do is we use these equations, but then we multiply our answer through by 100. If we ever needed to increase the efficiency, we need to increase the amount of useful energy transfer. Therefore, we need to minimize the amount of energy dissipated and wasted. The way that we could do this is things like streamlining, things like lubrication, try and stop frictions within the system, which could, of course, lead to energy transfers into less useful forms of energy. In physics, we learn about scalar and vector quantities. A scalar is a quantity which has magnitude only, so it only has a size associated with it, whereas a vector has both that magnitude but also direction. So in physics, we might often see vectors represented using an arrow, and the size or length of that arrow gives us an idea of the size of the quantity, and the direction it's pointing tells us the direction of it. Now at GCSE, of course, we learn about so many different things. Now, I've got this little table here just to summarise whether certain things you've learnt about are scalar and vector. So we need to know that speed is a scalar, whereas velocity is a vector. Distance is a scalar, whereas displacement is a vector. Time and energy are both scalar quantities as well, because they just have a size associated with them, not a direction. Whereas acceleration, force, and momentum, all of these things we will learn more about, are all examples of vectors. All forces are either contact forces or non-contact forces. Contact forces are experienced when objects are physically touching. Some examples of this include friction, where things are rubbing against each other, air resistance, where the air is in contact with you, tension, and also the normal contact force. And there's loads of other ones too. Non-contact forces, on the other hand, though, involve objects that are not physically touching. They're physically separated, and yet they're still experiencing a force between them. So some examples of this include magnetic forces. If you've ever held 2 magnets together, you'll be able to feel, even though they're not touching them, pulling together or pushing apart, even though there's no physical contact. As well as this, we have electrostatic forces and also gravitational forces. Now, don't forget that force, whether we're talking about contact forces or non-contact forces, are vector quantities. So they always have the magnitude, but also the direction. Frictional forces can cause surfaces to heat up. This can result in an unwanted energy transfer. To reduce this unwanted energy transfer, we can reduce the friction between the 2 surfaces. We can reduce unwanted energy transfers using lubrication. The atom is made up of 3 different types of particle. So we have protons, which are positively charged particles found within the central nucleus of the atom. Then we also have neutrons, which are also found inside the nucleus of the atom. Neutrons, however, have no charge. Now we might see this referred to as being neutral. Now that third particle found within an atom is the electron. Now electrons are negatively charged particles, and we don't find them in the nucleus this time, we find them in shells which orbit the nucleus. So you can see all this in our little diagram here, and we have to get very used to these diagrams and being able to label them accurately. In the electricity topic, we really do need to know the following electrical components. We need to be able to draw them and recognise them. So let's start off with the switch. We can see it open and closed. We know that a cell is two little parallel lines, one's bigger than the other, and a battery is several of these cells. Could be two, could be more than two. That's what makes up a battery, several cells. Then we have the lamp, which is a circle with a cross through it. A fuse, which is a rectangle with a line going all the way through it. A voltmeter is a circle with a V in it. And of course, we need to know that a voltmeter is used to measure voltage. An ammeter is used to measure current, and its circuit symbol is a circle with an A in it. A for ammeter. A thermistor is a rectangle with a tick through it. It's really important that we recognise that this rectangle with no line through it is a resistor. So different variations of these rectangles are going to be different types of resistors. So an LDR is a rectangle with two lines going towards the rectangle. You may see it with a circle around it, but you may also see it without that circle. And this is a light-dependent resistor. And that's why the arrows go towards it, because it depends on the light. So the light's shining on it. And it's a rectangle because it's a resistor. Then just a plain old resistor is simply a rectangle. A variable resistor is a rectangle with an arrow going diagonally through it. And a diode, which is a component which only lets current flow in one direction, is a triangle pointing in one direction with a line on the end of it. And sometimes this may have a circle around it, sometimes it may not, but they both represent a diode. And finally, we have an LED, or light emitting diode. This is just the same symbol that we had for a diode, so this triangle with a line on the end of it. But this time, because it's emitting light, we're going to point two arrows away from the diode to show it's a light emitting diode. So circuits can be connected in two ways. Of course, we have our series circuit where there's a single loop, and then we have our parallel circuits too. Now it's important that we know a few facts about series circuits and parallel circuits. So in a series circuit, we should know that the current is the same in each component. Now this comes down to the fact that current is the flow of charge. Imagine you've got cars driving around one loop. You're going to have the same amount of cars just driving through the whole loop, aren't you? They're not got anywhere else to go. So current is the same in each component. However, the total potential difference is shared between the components. And the reason for this is the fact that potential difference is actually the work done per unit charge. It's an energy, and so that energy is going to get shared as it goes through each of these components. Now, total resistance, on the other hand, is the sum of the resistance of each component. So we need to know that if we saw this example, for instance, the total resistance would be the resistance of bulb 1 plus the resistance of bulb 2. If we were to look at parallel circuits though, because we've got these different loops, again, if we think of those cars moving along it, when it gets to the little junction, there's two options for where the cars or the current goes. So the current will split between the different loops. Potential difference, however, is the same in each component. Remember, potential difference is the work done per charge, and each of those charges are just each going through one component. So it's exactly the same for every one of them, regardless of which route they took. Total resistance, however, in the parallel circuit is a little bit different. It's actually less than the resistance of the smallest resistor in the circuit. We don't, however, have to do any calculations for the parallel circuits at GCSE, just the series circuit. Why does adding resistors in series increase the total resistance? Well, this is just simply the fact that the current has more resistors to pass through. However, when we ask the question of why does adding resistors in parallel decrease the total resistance, it's a little bit more complicated. So the parallel loops are going to add an additional path for the current to flow through. And so more current can flow in total, even when the potential difference remains the same. Again, if we think of cars, for instance, this really makes a lot of sense. If another route opened up, then suddenly the cars and the traffic is going to flow much more freely, and therefore, just like the current, that flow will increase. And this is why adding additional paths for that current to flow through is actually going to decrease the resistance, leading to more current flowing. When charge flows in a circuit, we should know that work is done. Now we can calculate the amount of energy transferred by electrical work using the equation that energy transferred equals power times time. We can use the symbols here, E equals P times T. If we're using our standard SI units here, energy transferred will be measured in joules, which is a capital J, power is measured in watts, which is a capital W, and time will be measured in seconds, which is an S. As is the case with most equations in physics, we can write this in a triangle if you're not very confident with your math skills. To do this, we just put the P times T on the bottom. Remember, the bit with the times always goes on the bottom of a triangle, and an E on the top. Then, for whatever it is that you want to find, just cover it up with your finger and then use the triangle to get your rearranged equation. For example, power, P, equals energy over time. Here I've included a little top tip, and this applies to any equation, not just this one. We might need to convert minutes to seconds. We need to know that we do this by multiplying the minutes by 60. Alternatively, they might give you the time in hours instead. And again, in all likelihood, we're going to need to convert this into seconds. We do this by multiplying by 60 to get it into minutes, and then by 60 again. So multiplying by 3,600 converts hours to seconds so that we can use it in this equation. Now, it's not uncommon in physics, if the question's about an electrical appliance, that energy may be measured in kilowatt hours. Now, if this ever did happen, then we can use this exact same equation, however using slightly different units. The energy transferred is now measured in kilowatt hours. To be consistent with this, the power would be measured in kilowatts. And then finally, the time would be measured in hours. The amount of energy transferred can also be calculated using charge flow Q and potential difference V. Energy transferred equals charge flow times by potential difference, or using the symbols E equals Q times V. In this case, the energy transferred is measured in joules, which is a J, charge is measured in coulombs, which is a capital C, and potential difference is measured in volts, which is a capital V. If you are someone who struggles with your maths, we can just learn this triangle with the E on the top and the Q times the V on the bottom to help us with the rearranging side of this. Remember to use the triangle, cover up whatever it is that you need to find. Remember that the line means divide and the times mean times, and then you should be able to work out anything you need using that triangle if you're stuck. An electrical current is the rate of flow of electrical charge, and by electrical charge we could be talking about electrons or ions. We need to know the following equation for this. We need to know that charge flow is equal to the current times by the time. It can often be helpful to use this as the symbol equation just because it's quicker to write. In this equation, we represent charge flow with a Q, current with an I, and time with a T. So we can say that Q equals I times T. Now it's important that we know that charge flow is measured in coulombs, current is measured in amperes or amps, and time is measured in seconds. So if we ever have a time given to us in hours or minutes, we do need to convert it to seconds. Now, of course, everybody's math skills is slightly different. Some people struggle with rearranging this equation, and some people prefer to use the triangles. Now, all I care about is you getting all of the marks in the exam. I do not care how you get it at all, okay? Some teachers can be a bit snooty about triangles, but I just want you to get the marks. So if you do struggle with the algebra, this can be really helpful for rearranging the equation, say if we needed to find current. So the bit which is times together always goes on the bottom of a triangle. So we've got Q on the top, I times T on the bottom. And if we wanted to get I, all we'd need to do is cover the I with our finger and we can see Q over T. And so that's it. So the current is equal to Q over T. So now we know that, let's remind ourselves that for electrical charge and therefore current to flow, we need to have two things. We need a closed circuit, so no breaks in it, and a source of the potential difference. Now this could be a cell, it could be a mains power pack, it could be a battery. And what we'll find is that the current is going to be the same everywhere in a single closed loop. The current that flows through a component depends on two different factors. So the resistance of the component that it's flowing through and the potential difference through that component. We need to know the relationship between potential difference, current, and resistance. So we need to know that the potential difference is equal to the current times the resistance. And again, we'll find that using the symbols can just be a quicker way to write this down. And so we might see this as V equals I times R, where V is potential difference, it's the voltage, current is the I, and R is the resistance. So potential difference is measured in volts, which is V, current is measured in amperes or amps, which is a capital A, and resistance is measured in ohms, which is the Greek symbol omega. So again, we can use a triangle if you struggle with algebra here. Remember that the bits times together always goes on the bottom. So here we've got a V on the top and I times R on the bottom. And now you should easily be able to find whatever term you're asked to find. Now, for a given potential difference, we need to know that if we increase the resistance, we're going to decrease the current. And that's because if we increase the resistance, it's harder for that current to flow. It's a bit like making a pipe narrower. And so that means less current, less of this charge is going to be able to flow through the circuit. A bit like water flowing through a narrower pipe. In some resistors, we'll find that the resistance remains constant, even when the current increases or decreases. Now this is said to be an ohmic conductor. It obeys Ohm's law. Ohm's law tells us that the potential difference and the current are directly proportional to each other and therefore have a linear relationship. So what we'll see here is in an ohmic conductor, at a constant temperature, the resistance remains constant as the current increases. However, we'll find that the resistance of some different resistors actually changes as the current changes. So an example of this is a filament lamp. Now, filament lamps have tiny little wires within them, and the way that that lamp works is the current goes through them, they get hot and they start to glow, and that's how they illuminate the room. However, as the current increases, the filament is going to get hotter and hotter. If you imagine all of the atoms within that really hot wire, they're all going to be bouncing around the place. And what that means is that it's harder for the current to flow. Imagine trying to walk down the street and everyone's just running around the place. You're going to be knocking into people all the time. And you're not going to be able to walk as quickly. That's why as the current increases and the filament gets hotter, the resistance is going to increase. Now this doesn't obey a linear relationship. This shows a non-linear relationship. And actually the resistance increases as the current increases. Another example of a resistor whose resistance changes as the current changes is a diode. Now, a diode is a very important type of component. It's one where the current only flows in one direction. And the reason for this is that the resistance in the reverse direction is very high. Now, this is shown in our IV graph for the diode. We can see that in this negative direction, there's actually no current flowing. However, when the current flows in the positive direction, you can see that as current increases, the potential difference increases too. And an extra thing I just want to clarify and make sure that you know. This is going to be the same graph in LED as well. Don't be afraid and think because it's not diode alone, it's going to be different. We're going to see this exact same graph for LEDs and for diodes, so make sure you learn it. Another example of a resistor whose resistance changes as current changes is an LDR. LDRs, or light-dependent resistors, are particularly interesting because their resistance is affected by the light intensity. And as the light intensity increases, the resistance decreases. Now, this can make them really useful for lots of applications, such as lights which are sensitive to the dark. A good example of this is street lights. They only turn on when it starts to get dark, so perhaps they have an LDR in their circuit to ensure that this happens. The last resistor we're going to have a detailed look at here is the thermistor. Now, the thermistor is very similar to an LDR in how it behaves, except instead of light intensity, they're affected by temperature. So the resistance of a thermistor is affected by the temperature. And we'll see that as temperature increases, the resistance decreases. Now again, a bit like LDRs, this makes thermistors very useful for a lot of applications. An example of a use for thermistor is a thermostat. Most people have thermostats in their homes where they set a certain temperature for their central heating to come on when it gets a bit too cold. And this thermistor would be able to enable this to happen. Now we need to know how we can build a circuit to measure the resistance of a component, such as a resistor. However, it could be something such as a bulb, thermistor, or anything really. So the two key facts that we need to know is that we need to have an ammeter in series with this component to measure its current, and we need a voltmeter in parallel to measure the potential difference. You can see what this looks like in the diagram here. A very common 6-mark question that we're likely to see in the exam will ask us to investigate the IV characteristics of a component, and they may name the component, but remember the method is going to be exactly the same regardless. The first thing that we need to say is that we need to connect a battery to the component. Then we need to add an ammeter in series. And, of course, we then need to add a voltmeter in parallel. Next up, we're going to need to add a variable resistor in series with the component. Now, this is very important because we can use the variable resistor to change the potential difference. So, once our circuit is all set up, and make sure in the exam you draw this circuit just like I have here, but with the relevant component in place of this resistor. We then want to record the potential difference on the voltmeter and the current on the ammeter. Once we've done that, we now want to use our variable resistor to change the potential difference. We're now going to record the new values for potential difference and current. We're going to repeat this process by changing the potential difference using the variable resistor several different times until we get enough different pieces of data. Now we're going to do something quite clever. We're going to reverse the power supplies. And this can be done by something as simple as just changing the direction of the battery. Once we do that, we're going to repeat this whole process of changing the potential difference again using the variable resistor. But this is now going to give you negative values for current because the current's going to be flowing in the opposite direction. So once we've repeated this several times, we're now going to get all of our data and we're going to plot a graph of current against potential difference. And that is going to give us one of these graphs that we've seen earlier where we have a relationship between current and voltage. When there is an electric current in a resistor, there is an energy transfer which heats the resistor. When an electrical current does work against electrical resistance, electrical energy is dissipated as thermal energy to the surroundings. This energy transfer is caused by the collisions that occur between the electrons and the ions in that lattice. We may be asked how we can reduce unwanted energy transfers in circuits. One way of doing this is to use low resistance wires. Using low resistance wires will mean that there will be fewer collisions and less energy will be wasted through heating. We might also be asked what are some advantages of the heating effect of electric currents. And simply, there's lots of appliances that use this. There's toasters, there's kettles, electric heaters. All of these rely on that heating effect of electric current to work. We need to know how to calculate the power transfer in a device, and we can relate it to the current and potential difference using this equation. Power equals potential difference times current, or P equals V times I. Again, if your math skills are a little bit dodgy, you can always use a triangle to help you rearrange this when needed. The bit with the times always goes on the bottom, so you've got P on the top and V times I on the bottom. Now remember that power is measured in watts, potential difference is measured in volts, and current is measured in amperes or amps, which is that capital A. We can also calculate the power transfer in a device using the current and the resistance. Now this equation's a little bit trickier because it's power equals current squared times resistance. Don't forget that squared. So using the symbols, that would be P equals I squared, I for current, times R. And remember, of course, power is measured in watts, which is a capital W. Current is measured in amperes or amps, which is a capital A. And resistance is measured in ohms, which is that Greek symbol of the omega sign. When charge flows in a circuit, we should know that work is done. Now we can calculate the amount of energy transferred by electrical work using the equation that energy transferred equals power times time. We can use the symbols here, E equals P times T. If we're using our standard SI units here, energy transferred will be measured in joules, which is a capital J, power is measured in watts, which is a capital W, and time will be measured in seconds, which is an S. As is the case with most equations in physics, we can write this in a triangle if you're not very confident with your math skills. To do this, we just put the P times T on the bottom. Remember, the bit with the times always goes on the bottom of a triangle, and an E on the top. Then, for whatever it is that you want to find, just cover it up with your finger and then use the triangle to get your rearranged equation. For example, power, P equals energy over time. Here I've included a little top tip, and this applies to any equation, not just this one. We might need to convert minutes to seconds. We need to know that we do this by multiplying the minutes by 60. Alternatively, they might give you the time in hours instead. And again, in all likelihood, we're going to need to convert this into seconds. We do this by multiplying by 60 to get it into minutes, and then by 60 again. So multiplying by 3,600 converts hours to seconds so that we can use it in this equation. Now, it's not uncommon in physics, if the question's about an electrical appliance, that energy may be measured in kilowatt hours. Now, if this ever did happen, then we can use this exact same equation, however using slightly different units. The energy transferred is now measured in kilowatt hours. To be consistent with this, the power would be measured in kilowatts. And then finally, the time would be measured in hours. The amount of energy transferred can also be calculated using charge flow Q and potential difference V. Energy transferred equals charge flow times by potential difference, or using the symbols E equals Q times V. In this case, the energy transferred is measured in joules, which is a J, charge is measured in coulombs, which is a capital C, and potential difference is measured in volts, which is a capital V. If you are someone who struggles with your maths, we can just learn this triangle with the E on the top and the Q times the V on the bottom to help us with the rearranging side of this. Remember to use the triangle, cover up whatever it is that you need to find. Remember that the line means divide and the times mean times, and then you should be able to work out anything you need using that triangle if you're stuck. So mains electricity, which we have in all of our plug sockets, is an alternating current supply. Now what this means is that the current is repeatedly changing direction, and AC current is produced by an alternating potential difference. However, on the other hand, batteries that we use to put into our remote controls, for instance, or have in our phones or our laptops, they provide a direct current. Now in a DC supply, the current flows in only one direction, and it's produced by a direct potential difference. At GCSE, we need to know a bit more information about our mains electricity supply. So of course we know it's an alternating current supply, or AC. However, we also need to know that it has a frequency of 50 Hz and a potential difference of 230 volts. In the United Kingdom, most of the electrical appliances are connected to the main supply using a 3-core cable. Now this is a really safe system, so we're very lucky to have it in this country. Now these 3 different wires in the 3-core cable are colour-coded. And this is so useful because it means we can easily identify them and keep ourselves safe. So the live wire is brown, the earth wire is made up of green and yellow stripes, and the neutral wire is blue. Now, as well as knowing the colour of these different types of wires, we also need to know the role that they play and what potential difference goes through them. So the live wire is the most dangerous wire. It carries the alternating potential difference from the main supply. So it carries a voltage of 230 volts. Now the earth wire, which is made up of green and yellow stripes, is the safety wire. And this is very important because it prevents the appliance from becoming live. Now the only time that the earth wire will ever carry a current is if there's a fault in that appliance. But again, the purpose will be to keep it safe. So the potential difference normally then going through that earth wire is 0 volts. Finally, our neutral wire that's blue in colour, this is here to complete the circuit, and this has a potential difference of 0 volts. Now let's have a look at some other key features to the plug. So we can see here that we have a fuse in this plug. Why do we have these fuses? Well, the reason for this is that if the current gets too high, a thin wire inside that fuse will melt. And the importance of this is by melting, this is going to break the circuit. Now, of course, we know that when we break the circuit, electricity is no longer flowing, and this prevents the risk of electrocution, so it makes it much safer. Now, we can also see here we have a cable grip. Now, the importance of this is it holds the wires in place. Now, we'll see that the cable grip, as well as other parts of the wire, such as the flex and the actual plastic casing, is made of the material of plastic. Now, the reason why we use plastic is because it is a good insulator. However, the wires are made up of copper and they're coated in plastic. Now, the reason why we use copper in the actual wires is because copper is a good conductor of electricity. We need to know why a live wire might be dangerous even when the switch is open. And this is a really important question because, of course, if the switch is open, you might think that the current can't flow. However, if we were to touch the live wire, we could ourselves complete the circuit. And this is because we are, of course, in contact with the ground. And so that current will flow through our bodies into the ground. And so we could be electrocuted. And that's why that live wire is always dangerous, even when the switch is open. We also need to know what the danger is of connecting the live wire to the earth wire. Now, this is a very similar answer to what we just said. If the live wire came into contact with the earth wire, the circuit would be completed, and this increases the risk of electrocution or fires. So you can see there's so many important safety rules that we need to know when using plugs. However, they are designed to keep us as safe as possible. This topic starts nice and simple. We remind ourselves that magnets have north and south poles. North poles get represented by an N and south poles represented with an S. We should know that magnets will attract magnetic materials such as iron, steel, cobalt and nickel. We should know that like poles will repel and different poles attract. And of course, don't forget that magnetic forces are examples of non-contact forces. Permanent magnets produce their own magnetic field, which will always be there. Induced magnets, however, become magnetic in a magnetic field. Well, what is a magnetic field that we're talking about? Because we're going to use this concept a lot in this topic. A magnetic field is a region around a magnet where a magnetic material or another magnet will experience a force. And we represent these magnetic fields using magnetic field lines. We need to be able to draw and recognise the magnetic field pattern around a bar magnet. This diagram here shows it perfectly. So we will see that magnetic field lines will always point from north to south. This is really important. The closer the field lines, the stronger the field. And the magnetic field strength, you'll notice, certainly because they're closer together in this diagram, is at its strongest near the poles. As we move away from the magnetic field strength decreases. In the exam, we might be asked how to plot a magnetic field, and we can do this using magnetic compasses. So our first step is you're going to place the compasses around your magnet on a piece of paper. We will then mark the direction that the needle points onto the paper, and then finally we join these points together, and this will show the field lines. Magnetic compasses that we use to work out direction actually contain a small bar magnet. And when these magnetic compasses are not near to another magnet, they're actually going to line up with the magnetic field of the Earth. And this is really important because this tells us that the Earth has a magnetic core. It tells us that it's made of a material which is magnetic. Now actually the geographical south pole of the Earth is actually the magnetic north pole and vice versa. When a current flows through a conducting wire, a magnetic field gets produced around that wire. As you can see in these diagrams, they form little concentric circles around that wire. And the strength of the magnetic field that gets made depends on the size of the current going through the wire. So the bigger the current, the bigger that magnetic field, and also the distance from the wire. The closer to the wire, the stronger that magnetic field, and the further away you get, the weaker it becomes. We can also increase the strength of the magnetic field made by a wire by curling it into a solenoid, which looks just like this. The magnetic field around a solenoid actually ends up being very similar to the magnetic field around a bar magnet. The diagram here shows what that magnetic field around a solenoid looks like. You can see that inside the solenoid it is strong and uniform. We can see it's uniform because the magnetic field lines look evenly spaced. And we can also see that they're close together inside that solenoid, which is what shows that it's strong. The magnetic field is stronger inside the solenoid compared to outside because all of the small magnetic fields caused by the current in each of those turns will add up, causing a greater overall magnetic field. If we wanted to increase the strength of the magnetic field around a solenoid even more, we can add an iron core, and this makes an electromagnet. You may be asked in the exam, what are some advantages of electromagnets compared to other magnets? So one of the really important differences is that we can switch electromagnets on and off, simply by turning that current on and off. Now, you might think, why would this be useful? But if we look at the diagram here, imagine we're in some scrapyard or we're moving around old scrap cars or something. It's much easier if we can use this magnetic force turn on the electromagnet, attract our magnetic materials and move them using that force, and then turn it off and release them. Another great advantage of electromagnets is that the strength of the electromagnet can be adjusted simply by changing the current. If we increase the current, we get a stronger electromagnet, whereas if we have a permanent magnet, the strength of that magnet is just the strength of that magnet. We might see some applications of electromagnets come up in the exam. So let's have a look at this specific example of an electric bell and let's see how electromagnets can work. Now looking at this, if we close the switch, we will turn on the electromagnet because the current can flow through the circuit. Now of course, looking at the diagram, you can see we've got this iron armature. This is going to get attracted to the electromagnet and this is going to pull the hammer towards the bell and they're going to hit each other and it's going to sound the bell. However, of course, when this happens, we've broken the circuit and that turns off the electromagnet. This means that the armature is no longer attracted towards the magnet and it's going to move back to its original position. But by moving back to its original position, it's completed the circuit again. And so we're going to have this process just go back and forth, back and forth, back and forth on repeat, sounding that bell. Now this is one application. We could see loads of other ones too. So we just need to make sure that we can apply these principles to any little example they might give us. The national grid is the system of cables and transformers linking power stations to homes and factories to transfer electrical power. We're going to find two different types of transformer within the national grid. We're going to find step-up transformers and step-down transformers. Step-up transformers are found between power stations and transmission cables. Step-up transformers are really important. They're designed to increase the potential difference and therefore decrease the current. Now this ensures less energy gets lost through the heating of those cables. This increases efficiency. So more of that electrical energy is transferred from those power stations to the homes and the factories they're going to. Now step-down transformers, on the other hand, are found between transmission cables and homes and factories. Now step-down transformers decrease the potential difference to a lower and a safer value. It would be incredibly dangerous if we had potential differences as high as they were due to that step-up transformer entering our homes. The risk of electric shocks and fires would be very, very high. So we use step-down transformers, decrease that potential difference, and reduce those risks. Density is a measurement of how much stuff there is within an object. And we can calculate the density using the equation that density equals mass over volume. Now, if we want to use the symbol equation for this, we need to know that density is represented by the Greek symbol rho. Now, rho looks a bit like a curly P. So we can say that rho equals m over v. We need to know that density is generally measured in kilograms per metre cubed, mass is measured in kilograms, and volume is measured in metres cubed. Now, to be able to calculate density in the exam, we're often going to be asked to calculate the volume of different shapes. So we need to make sure that we can work out the volumes of cubes, spheres, cylinders, and cones. Let's remind ourselves of how we calculate these volumes and make sure you learn these formulas. So if we have a cube like we have here, we could use a ruler to measure the length of one of its sides, and we can calculate the volume by taking that length, x, and cubing it. So the volume of a cube is x cubed. A cylinder, on the other hand, we need to know both its height and its diameter. Its height we can use a ruler to measure, and the diameter we may use vernier calipers. Formula here is going to be pi times by d over 2 squared times by h. Or we may remember that from maths as pi r squared h, because of course the radius is a half of the diameter. If we had a sphere, we would take those vernier calipers again and use it to work out the diameter of the sphere. Then the volume would be calculated using 4/3 pi times by d over 2 cubed. Finally, we've got the volume of a cone. So here again, we need two dimensions. We need its height from its peak up to its base, and we need its diameter. So to calculate the volume of a cone, the calculation is 1/3 times by pi times by d over 2 squared times by the height. The particle model can be used to explain the different states of matter. So if we look at a solid, for example, we can see that its particles are arranged in a regular pattern, they're very close together, and they vibrate about fixed positions. Now, because they're very close together, solids are actually very dense. Now let's look at liquids. So liquids are found in a random arrangement this time. Particles are still close together, but the particles move around each other. Now, because these particles are still close, just not very close, they are still really quite dense. However, when we compare that to a gas, where the particles are still randomly arranged, but they're far apart now, moving quickly in all directions, it's the fact that they're far apart and therefore occupy a much larger volume that means that they have really quite a low density. In the exam, we need to be able to describe an experiment to find the density of an irregularly shaped object. So this could be something like a stone, something that isn't a distinctive shape which you have a formula to work out its volume for. So here we need to know this method. We'd start off by measuring the mass of the object using our standard top pan balance. And then we're going to get a displacement can like the one in the diagram. And we're going to fill it with water until the water is level with the bottom of that pipe, just as we can see here. We're then going to place an empty measuring cylinder under the pipe. Now we're going to be really careful here and we're going to drop our irregularly shaped object into the water. Now you can see in this example here, we've wrapped some string around the stone so that we can lower it in slowly. And the reason why this is so important is if we just dropped it in, then water would likely splash everywhere and we would lose some water, which would distort our results. So we'll place it in and then we're going to see water pour out of this tube. We're going to wait until the water stops leaving the displacement can. And then we're going to have a look at our cylinder, which was catching all of that displaced water, and we're going to measure the volume of that displaced water. Now that volume is the same as the volume of your object. So here then, we can use the equation for density, which is density equals mass divided by the volume, to calculate the density of that object. We could also be asked to describe an experiment to find the density of a regularly shaped object, such as a cube or something. And here the method is a little bit simpler in a way. First off, we're going to measure the dimensions of the shape. So we're going to use rulers to measure any lengths and vernier calipers to find diameters. We're then going to measure the mass of the object using a top pan balance. And then we're going to calculate the volume of the shape using those dimensions that we found. So here, if we had this cube, we'd measure the dimension of its length and we're going to cube it to get that volume. Then, now that we've got the mass and the volume, we're going to use the equation for density to calculate the density of the object. So in this case, we'd say density equals mass divided by that volume. We need to consider some potential errors that might arise when we find an object's density. Firstly, let us consider that different top pan balances being used by different people may have different calibrations. This could result in an error in measuring the mass. Also, we need to consider that different measuring cylinders might have different resolutions. One measuring cylinder might measure things to the smallest 1 centimetre cubed, another might just measure it to the nearest 5 centimetre cubed. That's the difference in resolution, and this could lead to different students getting different answers for those volumes. Finally, we can consider an incorrect setup of the displacement can. Maybe they didn't add water right to the very bottom of that tube, and therefore we might get different readings for the volumes because some people may have errors in their readings. Finally, we need to know that when talking about density, we might be given measurements for density in terms of grams per centimetre cubed, but we actually need it in kilograms per metres cubed, or vice versa. So it's useful to know the conversion between the two. So if we have a measurement in grams per centimetre cubed and we want to convert it to kilograms per metres cubed, we simply need to multiply through by 1000. Conversely, if we have a density in kilograms per metres cubed and we want to get it in grams per centimetre cubed, all we need to do is divide by 1000. During changes in states, mass is conserved. We need to know that changes of states are actually physical changes, they're not chemical changes. If we reverse the process, the material will regain its original properties. So if we think of some of these processes that take place, we should know that going from a solid to a liquid is the process of melting, whereas going from a liquid to a solid is freezing. So as we go back and forth there and we reverse those processes of melting and freezing, the material will regain its original properties. Likewise, when we go from a liquid to a gas, that's the process of boiling, whereas going from a gas to a liquid is condensing. Now, the final process that we need to know, one that we're probably less familiar with, is the process of sublimation. Sublimation is the process where the state changes from a solid all the way to a gas. And although we don't have quite as much experience of this, I'm sure that you can visualise opening a really cold freezer and it looks like steam is coming off of the ice. Now this is the process of sublimation. That solid ice is changing to a gas. Internal energy is the energy stored inside a system by the particles that make up that system. So this means that it's equal to the sum all of the kinetic and potential energies of all of the particles that make up that system. If we have a material and that material gets heated or cooled, the material would change in one of two ways. The first change is that that material might change temperature. And this means that there's a change in the thermal energy store of the material. So if you've heated up this material, it will increase in temperature because it has gained the thermal energy store. The second change that we might see is that chemical bonds may form or they may break between the particles. This means that there's a change in the chemical potential energy store of the material. If a material or a system sees a change in its temperature, the scale of that temperature change, it depends on one of three factors. Firstly, you've got the type of the material. Secondly, the amount of energy that's been put into the system. Finally, we've got the mass of the material. The reason why the type of material affects the scale of that temperature change is because different materials have different specific heat capacities. Now, it's really important we know the definition for specific heat capacity. Specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree C. We need to know this equation, which enables us to find the change in thermal energy of a system. So the change in thermal energy is equal to the mass times by that specific heat capacity of the material times by the temperature change of the system. As always, we might find it easier to use the symbols for this. Here though, we're going to see a triangle, which is known as the Greek symbol delta. So we've got delta E equals m times c, that's specific heat capacity, times by delta theta. Now in this case, those triangles or the deltas refer to the change of a substance. So we've got the change in energy, and delta theta is the change in temperature. So we also need to know the change in thermal energy is measured in joules, mass is measured in kilograms, specific heat capacity is measured in joules per kilogram per degree Celsius, and finally the temperature change is measured in degrees C. When a substance changes state, we'll see that the temperature doesn't actually change during this process. However, the stored energy within that substance, and therefore its internal energy, does change. So this is where we're introduced to a term, which is the specific latent heat. And we need to know that the specific latent heat is the energy required to change the state of 1 kilogram of a substance without changing its temperature. So we've got two different variations of specific latent heat. We've got specific latent heat of vaporization and specific latent heat of fusion. So specific latent heat of vaporization involves changing the state between liquid and vapor. I like to think vaporization, the vapor's in there somewhere, the gas, okay? So that could be going from liquid to vapor or vapor to liquid. We will still refer to this as the specific latent heat of vaporization. Then we've got specific latent heat of fusion, which this time is the energy required to change the state from solid to liquid of 1 kilogram of a substance. So again, specific latent heat of fusion could be talked about either going from solid to liquid or liquid to solid. It will be the same. We need to be able to calculate the energy required to change the state of material. So we need to know this equation. The energy for a change in state is equal to mass times by the specific latent heat. So the formula for this is delta E, remember delta means change, which equals M times L. The energy for a change of state is measured in joules, mass is still measured in kilograms, and specific latent heat is measured in joules per kilogram. In the exam, it's very common that we'll be asked to interpret heating and cooling curves. Let's take a look at this curve as an example. So here we can see that we've got this region here where we're in negative temperature, so it's very cold, and we can see that we have a solid. As we put energy in, we're going to see that this solid gets warmer and warmer and warmer until eventually it stops getting warmer and it stays flat on this curve for a period. Now the flat regions, these horizontal regions, are where we have changes in state. And so here in this case, we're going to go from a solid to a liquid. And all of that energy is going into breaking the bonds. Nothing is going towards increasing the thermal energy store. So then we go on. We've broken all of those bonds, and now we have a liquid whose temperature is increasing, until eventually it reaches another point. It reaches the boiling point of the substance. And this is where again it now goes flat and it remains horizontal for a while. And that's because all of the bonds within that liquid are going to be broken apart and it's going to now become a gas or a vapor. Now, when we put more energy in, what's going to happen is the gas is going to increase in thermal energy and therefore its temperature is going to increase. Now, this particular curve is looking at water. I know that because I can see that it has a melting or freezing point of 0 degrees and it has a boiling point at 100 degrees. So it's important that we know that water boils at 100 degrees and it melts at 0 degrees. And this is actually the only material whose melting and boiling point they expect you to know. Just water. But luckily we've got everyday experience of that, so I'm sure you're familiar with those facts already. In a gas, the molecules are constantly moving around in random directions. The temperature of a gas is related to the average kinetic energy of its molecules. And therefore, the higher the average kinetic energy of that gas, so the faster those molecules are moving, the higher its temperature. And this is why heating a gas, and so giving it more energy, leads to an increase in its temperature. If we had a gas in a sealed container, and so its volume is constant, and we increase the temperature of the gas, we would see that the pressure increases. Let's think about why. The particles are going to have more kinetic energy, and therefore they're going to be moving around the container more quickly. Now, if it's moving more quickly, the particles are going to collide with the walls of that container more frequently. This means that we're going to exert a greater total force on the walls of that container. Now, this increases the pressure. Now, temperature and pressure are directly proportional. If we increase the temperature by a certain amount, pressure will also increase by that same amount. So say if we doubled the temperature, the pressure would also double. We need to know how to convert between the Kelvin and the Celsius temperature scales. If we have the temperature in Celsius, we need to add 273 to get the temperature in Kelvin. Now, Kelvin is sometimes referred to as the absolute scale of temperature. 0 Kelvin is equal to minus 273 degrees C. And this temperature is very special because we refer to this as absolute zero. And at absolute zero, the average kinetic energy of all of the particles is 0, and the particles have stopped moving.
Ouch! This is why in some videos I've explained scratches.